invite Professor Badawi for starting the session.
This call is now being recorded.
Okay.
So welcome.
Thank you very much for the introduction and invitation. This is my first time I participate online, although I've been in India so many times. And this is, maybe, I don't know, if you want to count this one, it will be the 30th time. Can you hear me? Can you hear me?
Yes, Ayman, you please go ahead. You are also presenting the problem.
Okay.
Yeah.
All right. If you see me before, I didn't have a beard.
Yes.
So now I'm having a beard, and if you ask me why, because I try, there is something called the Trump COVID bleach that I had 2 liters of it, and as a side effect, I had a beard. Okay, anyway, the title of the talk is Ramsey number, partial order graph. And this is by Ayman Badawi and my co-author, Rosie Risner. Together, we end up writing this paper. This paper is submitted, but we did not hear anything yet. And what's all this about? Let me tell you. Okay, let's go. Yeah. All right. Okay, let's recall what we mean with Ramsey number. Ramsey number is, this is like one of the hard problems.
Ayman, sorry to interrupt.
Yes.
Yeah, I removed that person.
The present now is missing. So you please go ahead with again
Somebody
present.
is interrupted. I deleted that person.
What?
So you again do the present now option. You please again give.
Well, no need of that. Anybody wants to, you present that slide. Remember. Yeah, presentation is in the pupils slide.
There's a now.
Yeah.
Now it's working. Please go ahead.
Now it's
Oh, okay. Okay. So the Ramsey number, what does it mean? You can read this, but let me get to it. What does it mean in the language of graph theory? In the language of a graph theory, number is the minimum number of vertices such that undirected symbol graph of order V
okay.
a click number, a click of order M, or independent set of order N. That's exactly what we mean with RMN.
Except host.
Ramsey number MN. We are looking for the smallest number of vertices V, so that for all undirected symbol graph of that many vertices, we should have a click of order N. And what does click mean KM, complete graph with M vertices, or we should have independent set with N vertices. And this problem is like, many work on it. I'm giving you examples here, like a Greenwood. He showed that R336. What does it mean, R336? That the minimum number of vertices we need for undirected symbol graph in order to guarantee a complete graph with the 3 vertices or independent set with 3 vertices is 6. That's the minimum number of vertices of such graph in order to have one of these two. Independent, by the way, as you expect, what does it mean, independent set? Meaning every 2 vertices are not connected by an edge. So like you have either 3 where you form a triangle, or you have 3 only dot. Okay? All right, another example is R34. What is R34? Is the Ramsey number in order to have either a complete subgraph with the 3 vertices or independent set with 4. Okay? Here I am. So the minimum number is none. These results, you know, been done. This is like an old problem. It's still going on. I mean, this is a very easy to solve. In fact, it's not known in general. You know, because numbers get bigger and bigger. So we understand what we mean with 9 here. This is the minimum number of vertices of undirected symbol graph. I should have 9 vertices in order to have a subgraph that is K3 or independent set with 4 vertices. And the same thing they calculated R35. This number is 14. And 14 again, what does it mean? The minimum number of vertices we need so that undirected symbol graph will have either a complete subgraph with the 3 vertices or independent set with 5 vertices. And this number is 14. Remember that we are looking at the minimum number of vertices and we are considering all undirected symbol graph. Okay, and there is a calculation for 36 and 37. And the highest number I get, maybe they are more now, higher than that, like 8 is 28. 39 is 36. Remember what the 39 again means. R39 means the minimum number of vertices in undirected symbol graph, so that we either have a complete subgraph with 3 vertices or independent set with none. Okay. Is everything okay? Hello?
Ayman, everything is okay. Please go ahead.
Okay. So I continue.
Yeah.
Okay, so what we did in this paper, we did not consider all undirected symbol graph. We look at only the partial order graph, or another name is Hesse diagram. All of you may be seen Hesse diagram or heard of it, or partial order. And remember what we mean with a partial order set. It's a set with a partial order, we call it less or equal, where every element is less or equal to itself. And we have the anti-symmetric. That means if A less or equal B, then B should not less or equal to A if A and B are different. And the transitive, where if A less or equal B, B less or equal to C, then A less or equal to C. So this kind of partial order graph, and we want to calculate the Ramsey number for this type of graph. Okay? So you know what we mean with a partial order graph of A. That means we should have a partial order on the set of the vertices that satisfy the three axioms I mentioned. Okay? And as we go along, I explain, and this notation, we use R index, is it given here? But anyway, I will explain it when I need the notation. Okay. I will explain the notation when I get to it. Okay, so here is the Ramsey number of a partial order graph. As I told you, you have an order set and you have this simple undirected graph such that two vertices are adjacent if either A less or equal to B or B less or equal to A. So you have a partial order graph, a partial order set, and then you're gonna define how you're gonna connect the vertices. So how I gonna connect two distinct vertices? I connect them if either A less or equal to B or B less or equal to A, okay? This is how we connect the graph, okay? All right, so what gives you the first result? In fact, we look, if we try to find, because you expect that somebody already work on that, but we did not succeed to find exactly what we got, even though we still, suspect that this thing could be done, because, but remember that we only consider, we try to find the Ramsey number for all partial order graph or Hesse diagram. There is no restriction. And we end up with this theorem that the Ramsey number of the partial order graph, NM, we have symmetry, is equal MN and is equal to this number, N minus 1 multiplied with M plus minus 1 plus 1. So what that mean? If you fix like a 3 and 4 here, 3 and 4. So this will give you 2 and a 3 plus 1, so you get 7. So that means in order, so N is the 3 again, and M is 4. And we're looking at the minimum number vertices of a partial order graph, so that we can have a complete subgraph with 3 vertices or independent set with 4 vertices, because I said R3, 4. R3, 4 will give me the number 7 here. So that's the minimum number of vertices you need in a partial ordered graph. Okay? And of course you can, like if you want 5 and 6. 5, because here we have it in general for any N and M. Like 5 and 6, what does that mean? That means the minimum number of vertices we need is 4 and 5, 21. I said 5 and 6. 5 and 6, that means the minimum number of vertices I need for a partial order graph in order to have a complete subgraph with n vertices or independent set with m vertices is 21 vertices. Okay, So this was like, I consider the main result in, or at least if this is known, maybe we have a different proof for this result, but still things not clear. But our investigation did not lead to something like that for a partial order graph. Okay. Now we're gonna make use of that theorem to see what we can do, apply that in ring theory. Well, the first implication is what we call the perfect divisor graph. What is the perfect divisor graph? And this is, you need to read it carefully. You choose, of course, the ring is commutative, and you choose n bigger or equal to 2, and you set your set S to be of this element, M1, okay? And these element that you're gonna choose in the set, they need to be co-prime. What do I mean with co-prime? Meaning, you know, like the ideal generated by M1 R plus M2 R is equal to R itself, co-prime, okay? All of them are co-prime, okay? So, and then we take M to be the product of this element. So we take elements that are pairwise co-prime, and then M will be the multiplication of the elements in here. So what's the definition of perfect divisor of M? If D not equal M, and D is a product of distinct element of S. Okay, that's what we define a perfect divisor of, I'm checking if, yeah, I'm still on. A perfect divisor of M. Okay, it means that D is not M, and D is a product of distinct elements in here. So how we form the perfect divisor graph is the vertex set of the perfect divisor graph will be the set of all perfect divisor of M. Perfect divisor of M. And again, what I mean with perfect divisor of M, that's very crucial. D is not M, and D is a product of distinct element of S here, okay? And two vertices will be connected if and only if A is divide B or B divide A. This is how we connect vertices, okay? So this is the, it's very simple. You don't need to know much about, I mean, in fact, you know, you can define it for maybe you don't need commutative ring here, I don't know. This is like the perfect divisor of M here. And again, D has to be a product of distinct element. That's crucial. And how you connect the vertices by this condition. Okay, it turns out that this graph is a partial order graph. So that's what the first, then why? By defining this relation on the set V, we have A less or equal to B if and only if A equal B or A is a factor of B. Okay? This is how we define the partial order. And definitely these are distinct and co-prime that will guarantee that if A divide B, then B will not divide A. So maybe you wonder why we ask for these to be pairwise co-prime, because to make sure that we really end up with a partial order graph, because this is the condition how we connect two vertices. Okay? And it turns out you can calculate how many vertices this graph has. And this has to do 2 to the n minus 1. It depends on how many things you put here inside. To make it simple for you, like take R to be the Z. Z is the set of all integers, positive and negative. And you take a prime, like you take a 3, 5, 7, let's see, 11. 3, 5, 7, 11. How many primes I took? 3, 5, 7, 11. 4 prime. Then I can construct my pair. And then what I do, I multiply these numbers. Like I multiply 3 times 5 times 11. That's the number M. This is not Corona, I think. This is has to do with the smoking. Yeah. Okay. And how you connect the graph. Yeah. And how you, you are presenting. Okay. And how I connect, again, two vertices in here. So again, V will be the set of all perfect divisor. So remember, like 5 will be a perfect divisor. 3 is a perfect divisor. 3 times 5, 15 is a perfect divisor. 5 times 11 is a perfect divisor. Okay, 7 times 3 is a perfect divisor. How many of them will be 2 to the 4 minus 2? 2 to the 4, that means 16, minus 2, that will be 14. So you should have 14 perfect divisor when I have 4 element here, which I said 3, 5, 7, 11. We should have 14 different perfect divisor. And how we're gonna define the partial order, as I told you, either A equal B or A is a factor of B. And being these numbers, the one I selected, definitely they are pairwise, they are co-prime. Okay. What are the properties of this graph? Of the partial or perfect divisor graph on a set S. So you get the picture how I form this graph. It's the perfect divisor graph with M. And the following hold, that this graph is connected if and only if N is bigger or equal to 3. So you should have at least 3 things in here for the graph to be connected. The diameter of this graph, which is kind of interesting, maybe or maybe not, is 3. So the diameter is 3, fixed. Okay? Domination number, remember what's a domination number? Let me take you to graph theory. The domination number is the minimum number of vertices you need in a set so that every vertex outside the set is connected to at least one vertex in the set. That's what the domination number of a graph in general. So the domination number of a graph in general is exactly this, all right? Which is give you the minimum number of vertices you need in a set, the minimum, huh? There are many, dominating set, but we're looking for the domination number to be the minimum number of vertices in a set, so that every vertex outside the set is connected to at least one vertex in the set by an edge. And the domination number is equal to, if n bigger or equal to 2, and equal 1 if n equal 1. Okay? Yeah. Let's see. The girth, here the girth. The girth, remember, is the smallest cycle that you can form in the graph. If n bigger or equal to 3, then the girth, if n equal to 3, then the girth will be 6. The girth of this graph will be 3 if n bigger or equal to 4. And this graph, the partial order or the perfect divisor graph, is a planar, meaning that I can draw it on the floor without you cross the edges. I mean, this is a simple way to think of graph to be planar. I can draw it on the floor so that the edges do not cross. It will be planar if and only if n equal to 3. So these are one of the properties of the perfect divisor graph. Okay, what is the perfect divisor graph? Okay, here is the thing. You need to focus with me for a minute here. Remember, we calculate the Ramsey number for any partial order graph, all right? So it makes sense, maybe, if you try to calculate the Ramsey number for a specific graph, that is what? That is partial order. Maybe this number is maybe less. Of course, cannot be bigger, right? Because the Ramsey number will give you the number for any, when we consider all partial order graph, okay? But it turns out the Ramsey number for the perfect divisor graph is still the same formula, is equal to the formula for the Ramsey for any partial graph. Is not less, okay? So that mean is exactly equal to that. Again, remember you said, well, this is, you've seen that before. Yeah, but remember we calculated the Ramsey number for any, we consider all partial order graph, all, in all of them. Here I'm talking about the Ramsey number for this specific graph. So in many times, in fact, when you do the specific, maybe you get a smaller number, but turns out, no, for this particular one. Okay. Okay, the divisibility graph. So we introduced many graphs in this paper. One of them is perfect divisor. The divisibility graph is what you expect. You choose R to be cumulative and A be distinct element. Then we say A is a proper element of A. If A is non-unit, so A is non-zero, non-unit, mean A is a proper element, you know that. And here is the notation you need here. You see two vertical lines. This means A divide B, but B does not divide A. So whenever we say A double vertical line, like two of them, that means A is a factor of B, but B is not a factor. And we studied the divisible graph to be undirected, and two vertices not equal are adjacent if and only if A is, proper element of B, or B is a proper element of A. What meaning proper element? Proper divisor. That means A, as I told you, is divide B, but B does not divide A, or B divide A, but A does not divide B. Okay, under this, it become a partial order graph under this condition. Okay, it's clear, it satisfies the three axioms. So the divisibility graph also will satisfy. Okay, look, we look at the perfect divisor graph, and then we look at the divisibility graph, and both of them, they satisfy the same number, the Ramsey number for the partial order graph. Because again, you expect when you go to a smaller class of partial order, then this number will be smaller, but it's not. So here we study Ramsey number of all for all divisible graph, and it turns out that this number is what you see. Okay, what's the implication if you want to think about that? Like if you take Z, okay, all right, choose N and M bigger or equal 1. Like, okay, let me choose you and me, let's choose 4 and 5. And you set K to be, so I remember N is 4 and M is 5. So I have 3 times 4 plus 1, that means 13. And you take a subset where the number of the element in this set is bigger or equal 13. Okay? So what can we conclude? Remember, I have N to be 4 and M to be 5. And my set has at least 13 elements in it. Okay? What I took, 3 and 4? Is that what I took? Or I changed 4 and 5, I said. I think 4 and 5. Sorry. So N is 4, M is 5. If N is 4, then I have 3 times 4. Yeah. So N is 4 and M is 5. And I took a set, minimum, random set from Z with like 13 numbers minimum. Could be bigger. Then what can you conclude? You can conclude that we should have exactly, at least there are 4 elements in the set with this chain, that 4 element A1 up to A4, where A1 is a factor of A2, is a factor of A3, is a factor of A4. Remember, double, meaning a proper factor. Or what? Or there should be 5 distinct elements where you have none of them is a factor of the other. Wow. I mean, maybe you can have a proof for that using number theory, but this is a simple implication knowing the Ramsey number of the divisible graph. It's a very nice, for me, I like it. You can play with that. You know, like what's the minimum? Yeah, and you know, and so on. Like if I choose n to be 5 and m to be 6, n5, m6. Or, you know, let's have something nice, like 6 and 11. 6 and 11. N is 6 and m is 11. So what we have here, 10 and 5, 51. And you choose randomly a set with from the integers with at least 51 number. Okay? Remember, n is 6, m is 11. And you choose a random set from the integer with at least 51 numbers. Then what can you say? You should have 6 element in the set where A1 is proper a factor of A2, A2 is a proper factor, and so on. Okay. Am I okay? Hello?
No, Ayman, someone started presenting the thing. Wait, they will cut out. Someone wrongly present your presentation. Ayman, can you hear me?
Yeah, shall I continue?
Yeah, you continue.
You hear me?
Yeah, I hear you. Your presentation in the other side. You have to pin it.
Okay, the question is how many minutes left for me?
So how many minutes you may want?
I mean, you can tell me what's the maximum or the minimum, or
10 minutes maybe.
10 minutes, okay.
Yeah.
All right, so
to you.
yeah, I think that's enough. That will be more than enough.
Okay, fine.
Resume, I click. Is it okay now? Hello?
Okay, can you hear me?
Yes, can you hear me? Okay. All right, I continue.
Yeah.
All right. Okay.
Yes.
Okay, because I start reading these things. Seems I become familiar how to play with these things. Okay. All right. So you see this thing here, you can for fun, you can fix numbers n and m. And remember, the set has to be at least that many element in it. And then you guarantee that one of these things has to happen. And this is a nice, for me, it's very small result, but it's fun, really fun. Okay. And here is another closely related inclusion ideal graph. Maybe as you're familiar with it. This is a graph presented or studied by Akbari, Saeed Akbari. He's Iranian mathematician. He worked a lot on a graph attached to rings. And in this inclusion ideal, your ring need not to be commutative. Let R be a ring. Okay? And then they define what they mean with the inclusion graph. And it turns out the inclusion graph, the vertices is the set of proper left ideal. That's the set of vertices. And how you connect them? Well, we connect two vertices if I is inside J or J is inside I. And here this definition given by Saeed Akbari. This is the inclusion graph. So the inclusion graph, the set of vertices is the set of all distinct left ideal, proper left ideal. And then how you connect, this is how you connect. And it turns out that this graph, again, as you see, satisfy the same number. But you have to give a proof. You cannot say because it is a partial order, then it should have this number. No, that will be invalid proof. Because remember the Ramsey number we calculated for, we consider all partial order graph. Here I'm taking a special graph that's called the inclusion graph. So you expect the number be less, but it's not, still the same. The Ramsey number. Okay. As an application for that result, here what does it say? Like you choose, like, let's see, n is 5 and m is 11. Okay, and you choose a set S to be consist of non-trivial left ideal. And the number of this set, that's supposed to be cardinality of S, not A. I don't know what's happening here. Maybe I should have, yeah. It was and S be a subset of that, where the cardinality of S, I should say, or change S to A. Okay. All right. So we said 11 and 6. So you have 51. So you should have either 6 ideal with this inclusion, where I1 is, or you should have 11 ideal, none of them is contained in the other. Wow, that's interesting as an implication. There is another one on matrices, but I want to go to the last section. Idempotent. We introduced many graph, partial order graph, we call them. And here is what kind of interesting, maybe or maybe not. Yeah, here is a graph where for this particular graph, the Ramsey number is different from, because all the examples we did so far for perfect divisor, inclusion, divisible graph, the Ramsey number for each one of them is the same as the Ramsey number for the general one, which is n-1 times m-1 plus 1. Here is one class of partial order where the Ramsey number of this class is not really the general one. And here you choose k to be bigger or equal to 2, and bk will be like the positive, okay, kn0, like if you take k to be 3, here for k bigger or equal to 2, let's k equal 3. Then you take the positive multiple of 3, like 0, 3, 6, 9. This is what mean pk, maybe positive index by k. We take the multiple of k, including 0, but the positive one. And we can, after that, we can define a partial order on Z, where A less or equal to B, if and only if A minus B is in this set. So two elements in Z are connected by an edge. If A minus B is in this set, definitely this partial order, because A is connected to itself, A minus A is 0. And clearly, if A minus B is in here, that means A minus B has to be positive. So that means B minus A will be negative, so it will not be in the set. So with the second axiom is okay. What is the second axiom? If A not equal B and A less or equal to B, then B should not be less or equal to A, the partial order. Okay, so this is a partial order graph. This definitely, in literature, in fact, this graph, they call it the cone positive, K positive cone. K positive cone. Okay. And of course, as I told you, this relation will make the graph partial order graph. And here is the result. Let n, only if m between 1 and k plus 1, the Ramsey number will be the same formula. For m between 1 and k plus 1. Okay? If n and m between 1 and k plus 1, then we have the symmetry and we have the same formula. Remember what is k? K is the, like if you ask k to be 10, and this graph, we define it on Z, then two vertices in Z will be connected by an edge if A minus B is in multiple of what we said, K, 10. K is 10. It will be multiple of 10, but the positive one. So if K is 10 and you choose M between 1 and 11, then the Ramsey NM will be the same formula. As you see, if M bigger or equal to that, to K plus 1, then we have here, as we expected, we can have a smaller number. You see, if M bigger or equal to K plus 1, then the Ramsey number will be this. Okay. All right, I think these are some of the references on Ramsey number, and I thank you. And if you have any question, I know the answer, I will not hide it. Okay, I'm done.
Thank you so much, Ayman.
Thank you.
Thank you,
Thank
Professor.
So people are asking their doubts in the chat box.
In the chat?
Yeah.
Chat box.
Okay.
I will ask you, yeah. If there is some interesting question, I will let you know.
Okay. Okay, thank you. So far,
Yeah.
And
Excuse me, Professor. Formal vote of thanks by Organization Secretary. Hello.
hello.
Mic.
yes, Ayman. You please.
Mic on.
Hello, are you hearing?
Yes, I can.
Madam, we are hearing you. Please go ahead.
I'm there. சரி, நான் போய் பேசி சொல்றேன்.
ஒரு 5 நிமிஷம் இருக்கும்.
முடியுது.
முடிஞ்சிருச்சு.
Hello, sir. Good morning, sir. Sorry for
Yes.
that. Sorry for the disturbance. My mic
Yes,
is not working. Okay. So, a formal vote of thanks, sir. Hello.
Yes, please go ahead, madam. Please.
On behalf of School of Mathematics, Alagappa University, I am very grateful to Professor Ayman Badawi, American University, for this wonderful talk on Ramsey numbers of partial order graph and implications in ring theory. So it is very informative and useful for many researchers, sir. Sir, once again, I thank you, sir. Thank you very much, sir.
Well, thank you. Thank you very much.
Thank you, sir.
Feedback form.
Yeah.
Feedback form will be issued. Feedback forms.
I mean, how do you feel about the new technology?
Oh,
Hello?
yeah, I'm getting used to it now.
Yeah. Asir, we can.
You're used to them.
Uh,
Yeah, yes,
yeah,
yes.
the second,
Thank you, so much, Ayman.
second session will start at 2:30 today.
Okay.
By Dr. Asir.
All right.
Professor, you are also welcome to attend this meeting.
Sure.
Yeah.
2:30 Indian time. That means 1 o'clock.
Yeah.
Okay.
Yeah.
So thank you all.
All right. Thank you. See you all.
Yeah, see you. Bye.
Okay. Bye, Asir.
Yeah.
Yeah, bye. Bye.